Welcome back. In the previous video, we saw how a current is induced in a coil when the flux through it changes. And as promised, now we will look at how we determine the direction of that induced current. And that's where Lenz's law comes in. Okay, let's first recap Faraday's law. So Faraday's law states that an EMF is induced, epsilon is induced, which is basically potential difference. So potential difference, or EMF, which is written as epsilon, is induced in a conducting loop if the magnetic flux through the loop changes. So the flux has to change in order to induce an EMF. And Faraday's law gave us an expression for determining what that induced EMF is in volts. So when we take Weber over second, and if you simplify those units, you will see that it's nothing but volt, which is good because that's what it needs to be a unit of potential difference. And further, in order to get the direction of the EMF, we have to first figure out the direction of the induced current, which is given by Lenz's law. And here's the statement of the Lenz's law from your textbook. And it's only 2 sentences, but it's very confusing. So it takes some unpacking, which we will do in this video. So the first sentence is straightforward. It says that there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. Restatement of what we discussed as Faraday's law. The second sentence is a simple sentence, but this is where it takes some unpacking to fully understand. It says the direction of the induced current is such that the induced magnetic field opposes the change in flux. Lots of words there, lots of words you did not even fully understand the meaning of before you came to this class. So we need to take this sentence and really understand what it means. So what this is saying is that there is an induced current, and the induced current has a magnetic field. You know that every current has a magnetic field. The induced current is not an exception to that rule. So the induced current will also have a magnetic field, and so let's call that B induced. And what Lenz's law is saying is that the direction of this B induced will oppose the change in flux. I'm sure it's still not very clear. So let's break this down into steps. You know that I like to give you recipes for solving physics problems, and here's the recipe for using Lenz's law. So step 1, you want to draw the loop and the initial and final configurations of the loop and the external magnetic field. Since we are talking about a flux changing, there must be an initial and final situation that demonstrates the change. Then you want to determine the initial and final flux through the loop. So we know that the flux has to change to induce a current. So there's got to be an initial flux and there's got to be a final flux through the loop. And the change in the flux could be caused by a change in the magnetic field, the strength of the magnetic field going through the loop, or it could be due to a change in the area of the loop, or it could be due to a change in the angle between the area and the magnetic field, which changes the effective area that we discussed in the previous video. So by changing any of these 3 things, I can change the flux through the loop. So if the flux is changing, there will be an induced current. We'll call that I induced. And induced current, like all currents, has an associated magnetic field, and we'll call that B induced. Now, what we mean by the fact that the direction of B induced opposes the change in flux is this. So if the flux through the coil is increasing, we will take both situations. Either it's increasing or it's decreasing as it's changing. So if it's increasing, then the direction of the induced magnetic field will be opposite the direction of the external magnetic field. And because we said that one of the conditions that causes a change in flux is a change in the external magnetic field, B itself could be changing, and it could be changing in such a way that its direction changes as well. So in the special case that the direction of B changes between the initial and final values, then we want to use the direction of the initial B for this external. So I could just write here also initial to be clear. Most of the time we're not going to be having the direction of the external magnetic field changing, but if it does change, you got to remember to use the direction of the initial external magnetic field, and then the direction of the induced magnetic field would be opposite. that if the flux is increasing. And if the flux through the coil is decreasing, then the direction of B induced is the same as the direction of B external. Once again, we have the same rule that if the direction of B external changes between initial and final, just use the initial. And once we have the direction of B induced, we can use the first right-hand rule to get the direction of I induced. So we got to work a little backwards on this. We got to figure out the change in the flux. We got to recognize if it's increasing or decreasing, which will then give us the direction of the induced magnetic field, which we can use along with the first right-hand rule to get the direction of I induced. So there's Lenz's law. You might want to watch this one more time and make your own notes, because this simple sentence in the previous slide that basically said this, just a few words, the direction of the induced current is such that the induced magnetic field opposes the change in the flux. That's what we unpacked with all of these steps. Okay, let's take a quick example before we wrap this up. I'm going to take a situation much like what Faraday was doing. And let's say I place a circular coil on a table. So when we place a circular coil on a table and we are looking at the cross section, this is what we will see. So there is a cross section of wire here. There is a cross section of the wire here. There is a near side of the loop that we're seeing here. And then there's a far side of the loop that's behind it, covered by it. And let's say I hold, like Faraday did, I hold a magnet, a bar magnet here with the north pole on the top and south pole at the bottom. That's my initial setup. And for my final setup, I have the same coil sitting on the same table. So the situation hasn't changed. All I have done is drop the magnet closer into the loop. So now I have moved the magnet from its position in the initial situation to the final situation here. So I'm moving this magnet closer to the loop. So this magnet has an external magnetic field. That external magnetic field passes through the area of this coil. And the strength of the magnetic field is changing between the initial and final, so the flux is changing. Now our goal is to use Lenz's law and figure out the direction of the current in this coil, the direction of the induced current in this coil. So to do that, let's follow the steps that we just outlined. So the initial setup is here, and the magnetic field in the initial setup is going to be toward the south pole of the magnet. So I'm going to show it like this. All right, there will be presumably magnetic field lines that are this way and this way, but let's just kind of summarize everything as a magnetic field at the center, and it'll point up towards the south pole of the magnet. In the final configuration, I'm going to have the magnetic field in the loop again pointing up, but because the magnet is a lot closer now, I'm going to have a stronger magnetic field. So I'm going to call this B final, and this is B initial. Okay, so understanding what's going on here between initial and final, the strength, the magnitude or the strength of B in the loop is changing, and therefore the flux in the loop changes. Remember, flux was A times B times cosine of theta, where theta was the angle between the normal of the area and the magnetic field. And in this case, A is not changing, theta is not changing, but B is changing. So that changes the flux. Furthermore, I can determine what the type of change is. In this case, the magnet was brought closer to the loop. So the strength of the magnetic field increases, which means the flux also increases. So the next step we said is, because the flux is increasing, the direction of B induced is opposite the direction of B external. So I'm going to show the loop one more time over here. This is a circular current carrying loop that we're seeing the cross section. So in 3D, it would look something like this. And I'm just seeing it in the cross section here. So there's a near end of the loop, there'll be a far end of the loop on the back, and then there are cross sections here. And because the external magnetic field was pointing up, its direction didn't change. If it changed, I'd be using the B initials direction. So it might be a good idea to always use the B initials direction. And because the direction of B induced is opposite the initial external magnetic field, we know that the B induced has to point down. That's what Lenz's law tells us. So lastly, using our first right-hand rule, if the current in this left segment, cross-section, can either be going into the screen or out of the screen, and using our first right-hand rule, you can see that I gotta have my thumb pointing into the screen for my fingers to curl this way. And that's what I need for the magnetic field through the loop to be pointing down. So the current has to be going in over there. It has to be coming out over here. And when I have my thumb and my right hand pointing out here, the fingers curl this way, which means the magnetic field inside the loop goes down, which is what I want. So I have determined the direction of the induced current. Let me change colors here again just to clarify. So the direction of the current is going in there, out here, to the left in the near end of this loop, and on the back end of this loop, it's going to be going to the right. So I'll show that as a dotted thing. So there you have it. That's how you use Lenz's law to determine the direction of induced current in a coil. All right, so in this video, we learned how to use Lenz's law to determine the direction of induced current. And a way of stating the Lenz's law is that the magnetic field of the induced current always opposes the change in the magnetic flux that induced the current. And we saw what the steps of using that are. Thank you.